G'day again. Welcome back to Mathematics 302. Hope you're having a good morning or a good evening, as the case may be. Let's take these off and we'll get stuck into it. This is week 5, and this is a review. So we're going to have a review of work ready for assessment 1. Hope God is blessing you and you're ready to study. Here we go. So this is lecture 5, revision for assessment. All right. So cardinality and bounds. So there's going to be a few. These will just cover a bunch of different questions all over the place. I've just written some questions, which should cover most of what's in the test. A set is defined as S equals A, B, C, D. What is the cardinality of the power set S? You should be able to figure this out. 1, 2, 3, 4. You just do 2 to the power of 4 is 16. Pretty straightforward. Next one, define the bounds of e to the x, where x is an element of R, the reals. Again, fairly straightforward. Bounds in terms of sets are the y value. So where does the y go from and to? So the lower bound is 0 and the upper bound is infinity or unbounded. Simplify a plus b brackets c dash plus a b dash bracket, that's closing that bracket, b dash d using basic identities. I did give this question. What I've done here is explained it in a lot more detail so that when you get a similar question, you'll know what you can use, cancel, etc., etc. So here we go. Let's go through this step by step. So a plus b c dash plus a b dash b dash c. So what we're going to do is remove the outer brackets by distributing. So we're just going to get rid of that bracket to start with, and obviously that one. So now we've got b plus a plus b c dash b dash d. So this b dash d is just moved to there. B dash d is just moved to there. So now you've got a b dash d, and you've got the b dash and the b dash there. I think. Yep, no, b dash, b dash. Yep, okay. So then if we continue, so now what we're going to do is remove the remaining bracket by distributing that. So now we've got a c or a b b dash c dash d plus, and I'll put the b's together here, b b dash c dash d and a b dash d. So the b dash is there. They don't actually cancel, but it just means you've got one of them. So now here, what you're looking at is you've got a b b dash. So in set theory, b b dash equals b intersection b dash. It doesn't equal b plus, it's b intersection b dash. So what is it happens, which is the equivalent of b minus b dash? What happens if you intersect b, if we imagine a circle, and b dash is everything outside the circle, the intersection? Well, it's nothing, isn't it? So you've got everything in the circle is b, everything out here is not b, because it represents the rest of the sets or the rest of the world. So you've just got b, b dash, intersection is nothing. So it is the empty set. So here, this little bit here is the empty set. So now you've got empty set multiplied by c dash d. Well, the empty set intersection with that is 0. There's nothing there. So this disappears. So then we're just left with that. A b dash c dash d plus a b dash d. We can factorize out. This will be acceptable as an answer. That's fine. You can factorize it out here and take out a b dash d. So now here you've got c dash plus 1. Actually, you should. Whoops. Spoke too soon there. We're taking out you're taking out c, and this is one of this. So now you've got c dash plus 1. So in set theory, c plus. So the c plus is union. I should have written a union there. So we see union with the universal set, which equals 1. So this will just disappear, and you should get a b dash d. So I should have written that better there. So yes, you have to factorize that out, and then you get c dash plus 1. Anything plus 1 should be union. C union universal set, which equals 1. So that just cancels, and then you've got a b dash d. Hope that makes sense and is helpful for you answering questions in the test. De Morgan. So prove De Morgan's first law, where U equals A, B, C, D. I've just made up these sets. A equals AB and B equals D. So we want to prove it using these conditions. It's very straightforward. We've done this in the lecture. You're just doing the left-hand side versus the right-hand side of De Morgan's law. So A union B is AB union with D. So we're just doing the union of these two. So that gives us A, B, D. So yeah, that's pretty simple. So now we want A union B dash. So whatever's left over, well, that's just going to be C, isn't it? So the left-hand side equals C, A union B dash, or the B dash of the whole lot. That's the left-hand side of De Morgan's law. Right-hand side, so now we want to do what the right-hand side is. So A is AB, and hence A dash is CD. And then we want B is D, so B dash is all the rest, A, B, C. So now we want to intersect A dash B dash. Intersect those, and we wanted the intersection of CD, which is that, with ABC. So the intersection of those two is just C. So we've got the right-hand side is C, the left-hand side is C. I'm like, great. Therefore, De Morgan law, first law holds. Done. Pretty straightforward. Now here I probably should have written out what is De Morgan's law, but you know, De Morgan's law says this equals this. So proving it is really just taking these bits, going through the steps. Very straightforward. Okay, Cantor's theorem. For any set, the cardinality of its power set, the set of all its subsets, is strictly greater than the cardinality of the original set itself. If A is a set, then the absolute value of A is less than or equal to the power set of A. That's Cantor's theorem. This is Cantor's proof using the diagonal argument. So let's construct a matrix which is Sn by Sn, where we say n is countable. And here's our matrix. So it's Sn by Sn. Now we'll write down the elements of a diagonal, which is 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0. All right, there's our elements of a diagonal. Now we're going to invert those numbers. So we're going to 1, 0, 1, 1, 1, 0, 1, 0, 0, 1, 1. Right, we've inverted them. So since this sequence exists, like we can create this sequence, but it does not exist in the Sn by n matrix, which is countable. All right, it doesn't exist in that matrix because we've just inverted the diagonal. Therefore, the set of elements Sn by Sn is uncountable. So that's the very simple proof using the diagonal argument that the number of elements in an Sn by Sn is uncountable. Very simple, basic sort of proof. And this is the barber paradox. In a village, there is a barber who shaves all those and only those who do not shave themselves. Does the barber shave himself? We've been through this once already. If you say yes, he violates the rule that the barber only shaves those who do not shave themselves, and therefore he's no longer the barber. If you say no, then as the barber, he must shave himself, since he's one of those who do not shave themselves. So that's the paradox of the barber. And the question you're going to be asked is to link those three things that I've just described of point 4. Okay, the question is to describe each of those and then link them to figure out how they are linked together. And you should be able to Google that and do some research on that before the test. Equivalence. Write an equivalence in echelon form for this. So pretty straightforward. You've done echelon form before. So echelon form just means leaving a diagonal of whatever, turn this, this, and this, so that 2, 3, 2 into zeros. And that's what you want to do. Turn those into zeros, and that's echelon form. So if we just subtract, so 2 take away 2 is 0, 5 take away 4 is 1, 2 take away 1 is 1, then we get 0, 1, 1. So now I've got our first 0. We want these two to be zeros as well. So now I'm going to take twice the middle row away from that one. And now I've got 2 zeros. So we're going to 2 lots of 1 take away, sorry, 2 take away 2 lots of 1 is 0. 1 take away 2 lots of 1 is -1. So now I've got 2 zeros. I want to get rid of this 3. What I'm going to do is I'm going to multiply this by 3 and this by 2. So now I'll have 6. Whoop, I've got that out of order. My apologies. I've got 6, 12, 3. 0, 1, 1 stays the same, and 6, 0, 2. So now if I subtract, I'm going to end up with a minus 12 here. Oh no, what do? I'm now going to use the 1 and the 1 again. I'm going to take 12 lots of the center row and add it. So we add 12 lots there, I'll get 0. Add 12 lots of that one, I'll get 7. And so now I've got to echelon form. I had to do it a bit of a roundabout way there, but whatever way works so that you get 0, 0, 0, then you're done. Okay, so that's in a 3 by 3. If it's 4 by 4, you'd have another 1, 2, 3. Yeah, you'd have 3 more zeros to work with. Except 5 by 5, another 5, etc., etc. If it's just 4, if it's just 2 by 2, you only just need 1, 1, 0 to be there. Okay, and that's an equivalence for that in echelon form. List two elements from the equivalence class 1, 8. So here what you're looking at, this is an equivalence class. You're looking at the distance between these. 1 to 8 is 7, so you just want to think, okay, what is 7 distance apart? I'm going to go from 2 to 9 and 3 to 10. Done. Pretty straightforward. Equivalence relations. So the three relations, ARA, ARB implies BRA, and ARB, and if there is an ARB and a BRC, then that implies you can get an ARC. Okay, so there are our three equivalence relations. We want reflexivity, symmetry, and transivity, and they're the three descriptions. Relationships, in other relations, y equals x is 1 to 1, and y equals x squared is many to 1. So I'm just putting those two down there so that you can sort of stick those two in your head and go, okay, if I've got y equals x squared, it is many to 1. And then if I have any other ways, I can just think back to these two and I should be fine. We hope. You can go and practice the others yourself. An equivalence relationship for y equals x, so this is just a straight line. What you're looking for on the xy plane is just a parallel line. So you want y equals x. You can't change that 1x there, but you can change the location of the y-intercept. So y equals x plus 1 is a really easy equivalence relation. You can pretty much add anything here for any y-intercept, and you've got an equivalence relationship on the xy plane. An equivalence for 7 mod 12. Well, we just want anything that turns into a 7 when you mod 12. And I just thought, okay, just 7 plus 12 is 19. So 19 mod 12 is going to give you 17, going to give you 7. That's the simplest one I could think of. You can do any other number for 7 mod 12. I probably should write 19 mod 12 there. But any other thing gives you an equivalence. Is there calling an equivalence relation? Why or why not? Here we go. Now I've got our diagram. I'm going to have to move my image up there. There's our diagram. Is it an equivalence relation? So what we're going to do is go through these things. We want ARA. So obviously ARA. So A goes to A, B goes to B, C goes to C. Tick, we've got ARA. Every element in the set relates to itself. If I start at A, I can get to A, B to B, C to C. Great. ARB implies BRA. So if I go A, B, that means I should be able to go B, A. Yep, great. If I go C, B, then I should be able to go B, C. Great, tick. So I can do that. If ARB and BRC, then I can get ARC. So if I go from A to B, then I go from B to C, then I should be able to go from A to C. Bom, bom, I can't. So ARA is a yes, ARB to BRA is a yes, and ARB and BRC do not imply ARC, no. Bom, bom. So no, it's not an equivalence relation. It's almost, but not quite. Hope this is helping you. Partition, list a partition for the set x equals 1, 2, 3, 4, 5. Any partition. So you want just any partition of this. So you just want to split this up. So there you go, 1, 2, 3, and 4, 5. Done. That's a partition. Another one could be 1, 2, 3, 4, 5. Now, any split up of these, as long as you're including all of the elements, you're fine. Why is 1, 2, 3, 3, 4, 5 not a valid partition of the set? X equals 1, 2, 3, 4, 5. Really easy and really obvious looking at that. There's 5 elements there, there's 6 elements there. 3 is contained in more than one block. So it's here and it's here. So, yeah, that's not a valid partition. Set laws and things to remember. I thought I'd write this out and sort of plonk it all in point 8. Set laws. So your set laws, empty set union with X is X. Empty set intersection with X is the empty set. X union with the universal set, looks a bit weird having UU there, but I'm speaking it, so it's pretty obvious what it is. It probably needs to be a better way to write UU. Anyway, X union with the universal set is the universal set. X intersection with the universal set is the X, is whatever the set X is. Multiplication is intersection. So if you have xy, that is X intersection y, which I tried to explain probably in the first slide. And addition is union. So X plus Y is X union Y. Complement laws. X union with X dash is the universal set, and X intersection with X dash is the empty set. And we did do that one earlier. Empty set and universal set laws. The empty set dash is the universal set, and the universal set dash is the empty set. De Morgan's law, which we already did, A intersection B dash equals A dash union with B dash, and which we did prove with an example. The double complementary law, X dash dash equals X. So that's fairly obvious. Topological spaces, point 9. Are the following topological spaces of 1, 2, 3, 4? If no, give a reason. Empty set and 1, 2, 3, 4. Is that a topological space? Answer, yes. This is a trivial case of an empty set and the full set. So you've got empty set, full set, that's it. So that is the most basic topological space you can get. Empty set, 1, 2, 3, 4, and 1, 2. Is that a topological space? Yes. The union of, so you test with union intersection. That's how you're testing. So you know this is true. So we're going to test this 1, 2. The union of 1, 2, 3, 4 and 1, 2 is 1, 2, 3, 4. And that's present, that exists. So the union of those two exists. The intersection of 1, 2, 3, 4 and 1, 2 is 1, 2. And yes, that intersection exists. So if you've got a union and an intersection of each of the subsets within it, then it's a topological space. Okay, empty set, 1, 2, 3, 4, and 1 and 3. No, the union of 1 and 3 is missing. So I've got to have an intersection. I can do intersection that and that. I can get 1. Union, I get all of that. Intersection with that and that, I just get 3. Union, I get all of that. Union of 1 and 3, I don't get because I should have 1, 3. So I should have like a 1, 3 there. So that is missing. So I need to be able to have that the intersection 1 and 3 is the empty set. So that's there. So the union is missing. So no, it's not a topological space. If I put in brackets 1, 3, then it would be a topological space. Okay, prove that a set is closed if and only if it contains all of its limit points. We've done this one previously. A question like this or similar to this will be in the assessment. Suppose A is closed, then by definition the complement AC is open. Suppose we have a limit point x of A that is outside of A. In other words, x exists inside of A complement. Therefore, there's a sequence AN in A where AN approaches X, i.e. AN converges to X. But, problem, there exists an X inside of the A complement, and A complement's an open set, but that means there exists some point in X in the set AC. Now, by definition of open set, there exists a neighborhood of points, around, which are close to and around any point in the open set. So therefore, there exists an X plus alpha, which is inside of AC, and there exists an X minus alpha inside of AC. That's assuming like just on a straight line, plus and minus. I mean, it could be surrounding it. but we're just going plus and minus here to prove a point, and where AC is the open set. So that exists in there, which means it causes a contradiction, and my image is in the way, because the sequence in A, which we're saying converges to X, can't get to X. You literally can't get there because there's a bunch of points around it. In this case, we're saying there's an alpha on the left, oh, sorry, a plus alpha on the right and an alpha on the left, which means you can't get to it because the definition of open set says a neighborhood of points surrounding every point. Okay? Hope that's helpful for you. Therefore, A must contain all of its limits points because this is impossible. And there's a connection on YouTube. Okay, infimum supremum or supremum and infimum. Find the supremum infimum of n, where n's a natural number, of n squared less than 37, making it really easy for it. Whoop. Did I put an answer there? I didn't put an answer. Oh my goodness. Okay, that should be n equals 6. I didn't put an answer. Okay, n equals 6 for the supremum and n equals minus 6 for the infimum. Okay, right. Well, there we go. It's a quick way to finish that screen. Sequences. Consider the sequence of intervals an equals 0, 1 minus n. Is this increasing or decreasing? And you've got 0, 0, 0, 1, 0, half, 2/3, 3/4. And this is an increasing sequence, okay? So which we've seen before. What is the limit? The limit is n approaches infinity. Prove the following sequence. So that's just the first type of question. This is also with sequences. Prove the following sequence has a limit and determine what that limit is. So if a1 equals 2, an plus 1 is an plus 5 over 3 for n greater than or equal to 1. Now this is one I did previously. You'll notice a lot of repeats here in this lecture of examples. That's because I didn't want to give away the actual question in the test and accidentally write the question in the test in this practice section. So I thought I'll be very careful. I'll just copy and use the previous ones I've done. First, prove by induction that an is less than an plus 1, i.e. a smaller term is less than the bigger term, is increasing. So given a1 equals 2, then a2 equals a1 plus 5, which is 7 on 3, and 7 on 3 is greater than 2. Therefore, it's true for n equals 1. Now assume it's true for n equals k, so you just literally write it out with a k, put a star next to it, or a dot, or whatever you like, then show it's true for n equals k plus 1. So we want to show that is less than that. So we're just going to write out those two formal definitions, get rid of this 5 on 3, so plus 5/3, cancel, cancel, get rid of the divided by 3, or you can, to multiply by 3, you get a k plus 2 is less than or equal to a, k plus 1 is less than or equal to a k plus 1, which is true since that's our assumption. So that's really easy. Prove the following sequence has a limit and determine what that limit is. So now, second, we're going to show it's bounded. Take one term at a time. We're just going to go a1 is that, a2 is 2.3, a3 is that, a4 is that. So we're looking at, like I said, you can pick an earlier term, but 3 is good. It's not going to reach 3. So it's bounded, as it's obvious it will be less than 3. So using induction, a1 equals 2, which is less than 3. That's true. AK, if we put in AK, that's less than 3 if we're putting in whatever the AK is. And here what you're doing is you're putting in the limit. You're putting in that limit as 3 plus 5 over 3 is 8 over 3 is less than 3. So you're saying that if it got to the limit, it's still less than the limit. So it follows that AK is less than 3 for all n. Lastly, find the limit. And we're going to use exactly what we just used then, which is putting in the limit. So the monotone convergence theorem says there must be a limit if it converges. We can say that previously we just put in the 3. We're going to put in L now. So L equals L plus 5 over 3. Multiply this out. So 3L equals L plus 5. To take off the L, L equals 5 on 2. And that's our limit. So if you get something like this, dooby-dooby-doo, I wonder if you will, that's the process of what you're going to do. It's pretty straightforward. That's it. All the best in the assessment. God bless you. Stay safe. There is one question in there I have not gone through in the test. It's the second last question. So hopefully it's a challenge. If you're sort of in genius mode, you'll go, oh, I can do this and knock it out of the park. But hopefully that one question is a little bit of a challenge, not very long. Try to put one question in there, which is that you sort of, oh, okay, that's interesting. Okay, bless you heaps. All the best. I'll see you soon.